This study investigates the deductive reasoning ability of large language models, focusing on how their performance evolves with size, the impact of reasoning depth, and the influence of training setup specifics. The research uses the closed-world variant of the rule-takers dataset, which includes groups of 100,000 randomly generated theories for depths ranging from 0 to 5, written in structured language. Two special groups, Nat Lang and Bird's Electricity, contain examples written freely in natural language, adhering to principles P14. The study evaluates 16 models, ranging from 117 million to 175 billion parameters in size, and tests their deductive reasoning ability at depths 0, 1, 2, and 3. It is observed that notable differences in model performance arise from different training setups, and that the deductive reasoning ability generally increases with model size, except for OpenAI GPT-3 and GPT-3.5 models. The results indicate that the performance of the models does not decrease with the length of the deductive chain needed to reach the conclusion, with the exception of OpenAI GPT-3 and GPT-3.5 models. This suggests that these models may be less capable of handling complex deductive chains. The study also explores the influence of training setup specifics on model draw, considering factors such as the proportions of different languages used, the use of code versus pure natural language, and the emphasis on edited sources over spontaneous language. The findings suggest that the role of the training setup is not negligible, and certain setups can significantly impact the model's draw. Overall, the study provides insights into the capabilities and limitations of large language models in terms of deductive reasoning, highlighting the importance of model size, reasoning depth, and training setup specifics. It also underscores the need for further research to understand how to improve the draw of these models, particularly in handling complex deductive chains and leveraging diverse training setups. The study evaluates the deductive reasoning ability, draw, of large language models, focusing on their performance in answering questions that require different depths of deductive reasoning. It uses a dataset consisting of theory, leading examples, and a question to be answered. The models are provided with inputs in the form of a concatenated string, including the theory, leading examples, and the question. The evaluation includes both open-source models and OpenAI GPT-3 and GPT-3.5 models. Open-source models have between 117 million and 66 billion parameters, sorted into three families based on their training setup: OpenAI GPT-3.5 models, Bloom models, and Facebook OP models. The results show that larger models generally exhibit higher draw, but this effect can be compensated by choices made in the training configuration. For instance, Bloom 560 meters outperforms larger Bloom models and the Bloom setting as a whole, which in turn outperforms much larger OPT and GPT-2 XL models. This may be due to the multilingual training setup of Bloom models, which includes multiple programming languages, in contrast to natural language English used for GPT-3.5 and OPT models. The performance of OpenAI GPT-3 and GPT-3.5 models decreases as the number of deductive steps required to reach the conclusions increases, as seen in Figure 1. The study concludes that the subject of deductive reasoning ability in large language models warrants further examination from a wider set of angles. However, the work only considers the token probabilities directly as provided by the generative models, which could potentially be improved by fine-tuning the language modeling head. Here is a combined summary of pages 5 and 6. The authors reference various prior works on neural language models, transformers, and common sense reasoning. These works investigate how pre-trained language models capture factual knowledge, perform reasoning tasks, and generate implications and abductive statements. The rule-takers dataset is introduced, which consists of theories written in structured language and natural language. The structured language theories contain rules and statements about entities and their properties, such as, if something is kind then it is big. The natural language theories are paraphrased versions of the structured language theories, using everyday language to express the same rules and statements. The authors provide examples of input instances based on the theories, which are used to evaluate the model's ability to reason and answer questions. For instance, Figure 2 shows a theory in structured language, where the question, is Aaron round, has a depth of 0, is Aaron big, has a depth of 1, and, is Harry young, has a depth of 3. Figure 3 illustrates a theory in natural language. Where is Dave green? Has a depth of 0. Is Dave kind? Has a depth of 1. And is Dave young? Has a depth of 3. Figure 4 shows an input instance based on the theory from Figure 2, with leading examples of depth 0 and the question to be answered by the model. These input instances are designed to test the model's ability to perform reasoning tasks, such as deduction and abduction, and to evaluate its ability to capture factual knowledge and generate implications. The authors aim to investigate how well large language models can reason and answer questions based on the given theories, and to explore the potential of using these models for common-sense reasoning and knowledge acquisition. Here is a combined summary of pages 7 and 8 of the research paper. The evaluation results of open-source models on natural language datasets are presented in Table 2. The models are listed by family, with sizes ranging from 117 million to 7.1 billion parameters. The binary accuracy metric is used, displaying the proportion of correct answers relative to the baseline coinflip performance of 50%. The leading examples, less, used or either none, no leading examples provided, or YNR, examples of yes, no, and a random question. The results show that the Bloom 7B model achieves the best overall performance on the NatLang dataset with a score of 0.27, while the OPT66B model performs best on the BIRDS-elect dataset with a score of 2.49. The evaluation results of OpenAI GPT-3 and GPT-3.5 models on structured language datasets are presented in Table 3. The models are listed in order of their growing size, ranging from 1 billion to 175 billion parameters. The depth metric is used, with values ranging from 0 to 3, indicating the level of leading examples provided. The results show that the GPT-3.5 Da Vinci model achieves the best overall performance, with a score of plus 26.28 at depth 0, and the GPT-3 Curie model performs best at depth 1, 2, and 3, with scores of plus 7.09, plus 8.68, and plus 8.93, respectively. The evaluation is limited to YNR leading examples due to the restricted information available through the OpenAI API.